My name is Alex Kiser, and I'm a PhD student working at Texas A&M. Thank you all for listening to my talk about the effects of flow and mussel species traits on the occurrence of rare mussels within the West Gulf coastal plain. All riverine aquatic organisms are subject to the natural flow regime of the system it resides in. This natural flow regime is dictated by the changing quantity and timing of flows through time, and include both high flows and periods of drought. A number of flow metrics can be used to describe the natural flow regime, as the timing of events, magnitude, frequency, duration, and rates of change from one condition to another. This variability, and on a grander scale predictability, determine the aquatic habitat template. This template dictates the conditions that an organism must adapt to or evolve with in order to continue to survive in this area. These adaptations develop into various traits that enable an organism to survive and reproduce within the confines of the habitat template. These traits can vary depending on the habitat and range from fast, short lives with emphasis on high reproduction to long-lived, low-fecund species that may wait decades to reproduce. These traits make up the reproductive and life history strategies of an organism and have been described by researchers as R versus K and equilibrium versus opportunistic species. Because the organism have evolved and adapted to these natural flow regimes, flow alteration poses a potentially dramatic effect to native fauna. Flow alteration from landscape change, impoundments, and climate shifts can dramatically shift the timing, magnitude, and predictability of natural flows. This causes a shift in the habitat template to one that may be unsuitable to local fauna, leading to declines in abundance, health, and even extirpation. Given the dramatic landscape alteration that has happened in eastern Texas, the objectives of our study were to identify change in flow parameters over time, identify the effects of changing flow parameters on our focal species, and use species traits to better understand how mussel occurrences and at a larger scale, how community structures are shaped by flow. To do this, we focused on 4 river basins in eastern Texas, the Trinity, Sabine, Cypress, and Neches rivers. These river basins offer a natural testing gradient for flow alteration. The Trinity River is heavily impounded and subject to large-scale urbanization from the Dallas-Fort Worth area, while the Neches River offers a better look at a lowly modified river with few dams and a higher percentage of forest land within the watershed. The Sabine and Cypress rivers offer an intermediate level of flow and landscape alteration. Additionally, these 4 basins contain 3 species of mussels that are listed as state-threatened and petitioned to be federally listed. Botomylus amphicanus, or the Texas heel splitter, is a relatively short-lived species with an expected lifespan of 5 years and is reproductively active within the first year. It is a highly fecund species and considered a long-term brooder, holding its glaucidia over winter and spawning in mid to late summer. The Texas heel splitter is found in 3 of our 4 focal basins, and based on its life history characteristics, most closely represents an R-selected species. Pleurobiema redelli, or the Louisiana pigtoe in contrast, is a long-lived species with an estimated lifespan of 40 years, and based on congeners is likely first reproductively active between 4 and 12 years. Louisiana pigtoe is a short-term brooder that spawns in late winter and releases its glaucidia in mid-spring to early summer. It closely represents a K-selected species with a long lifespan and lower fecundity overall, and is primarily found within the Neches River Basin. The last of our focal species is Transilla macrodon, or the Texas fawnsfoot. Similar to the Texas heel splitter, it has a shorter lifespan of 8 to 10 years, is moderately fecund, and a long-term brooding species, and based on these characteristics, it would best be classified as an R-selected species. It's found within the Trinity River Basin and 2 others outside of our study area. Due to low observations within our study area, we paired a closely related congener species, Transilla donisformes, which also exhibits similar life history characteristics and range. Our location and temporal data came from the Mussels at Texas database, an online data collection from museums, university collections, and private contractors that represents historical data from the late 1800s to present. For our focal species, the primary data collection was from 1968 to 2018. Due to inconsistencies in collection methods, we only looked at presence versus absence of a given area and did not assess abundance. Based on mussel locations, we collected stream gauge data from the USGS stations that were within 20 river kilometers of each mussel observation. This range gives us the best availability of flow data within a reasonable spatial extent. We then standardize all flow gauges by dividing the parameters by the mean annual flow of the station. This allows us to compare between basins and offer an easier metric for setting management goals later on. We further merited the gauge data to ensure that it contained at least 15 years of daily flow and covered at least 70% of the temporal range of our collections. We then ran the gauge data through the NatureServe's Indicators of Hydrological Alteration package to obtain flow metrics through time in 67 different variables that describe the timing, magnitude, frequency, rate of change, and duration of flow. Using this data, we used the IHA trend assessment tool to determine change in flow parameters over time at a station. We then screened the variables and removed those that were incomplete for all years. To reduce model overfitting, we removed variables using variance inflation factors to screen for multicollinearity with a coefficient greater than 0.8. We then used random forest models to predict occupancy based on flow parameters. We performed initial testing and further reduced the variables that fed each final model by removing those variables where a mean decrease in accuracy was equal to or less than 0, as these variables did not contribute to overall model accuracy for the species. We then assessed the final models based on a series of metrics such as out-of-bag error, sensitivity, specificity, and kappa. Then, based on our final model outcomes, we used the mean decrease in accuracy and mean decrease in Gini to determine variables of most importance to model accuracy, and by proxy those that contribute most to the predicted occupancy of a species within an area. Based on these variables, we created partial dependency plots, which show probability of occurrence over a range of variables, with lowest regression lines at 95% confidence intervals. In total, we analyzed 28 gauges that met the temporal and spatial extent needed for inclusion. Of those, 26 stations showed significant change in at least one flow parameter over time. The Trinity River was the most heavily impacted and showed significant changes in multiple parameters that represented base flows, timing, magnitude, and frequency. The Neches River showed significant changes in some parameters, but overall was the least changed and was the only basin with stations that did not show significant change over time. Based on the temporal and spatial criteria, we had 112 observations of Randklev associated with 11 gauges, 94 observations of Amphicynus with 12 gauges, and the combination of Macrodon and Doniciformes had 37 observations at 10 gauges. Model accuracy for Amphicynus was high with an out-of-bag error of 10.7% and high sensitivity, specificity, and kappa. Based on mean decrease in accuracy and mean decrease in Gini, the variables that most contributed to presence were base flow index, one-day minimums, date of the minimum flow, and flow predictability. As you can see here in the figure, there's a distinct threshold for base flow index and one-day minimum flows, where the predicted occupancy is higher above a ratio of 0.15 of the mean annual flow. We also see that as date of minimum flow increases, predicted occupancy drops significantly. Based on our data, Amphicynus also prefers rivers with greater flow predictability over time. Randklev had moderate accuracy with an out-of-bag error of 21% and moderately high sensitivity and specificity and high kappa. Based on mean decrease in accuracy and mean decrease in Gini, mean flows for December and July, low pulse count, and low pulse duration were the most influential flow parameters for predicting occupancy. Based on our results, you can see that Randklev does best with higher monthly flows in December and lower flows in July. This could be due to reproductive needs, with need for lower flows during periods of glaucula release. We also see this with higher probability of occurrence with increased duration of low flow events, but there is a threshold where number of low flow events has a negative impact on presence. Team Macrodon had the lowest out-of-bag error at 3.5%, with high sensitivity, specificity, and kappa. Based on the mean decrease in accuracy and mean decrease in Gini, one-day minimums, data maximum flow, base flow index, and mean July flow were most important variables to determining occupancy. With Team Macrodon, we see an increased probability of presence with higher minimum flows and base flow conditions. Similar to P. Randklev, though, we see the importance of timing of low flow events and the need for lower flows in July. While base flows are important, these results indicate that there is a need for seasonal timing of high and low flow events. While some of our data is nuanced and needs further analysis, there's a clear trend that can be identified for several parameters. For P. amphicanus, there's a threshold of probability where occurrence drops significantly below a ratio of 0.15. This indicates that streams where base flow drops below this level would be predicted as unsuitable, or if a stream were to dip below this level, it could lead to declines or extirpation of this species. This method could be useful for water resource managers who seek to prioritize management of threatened species by identifying certain threshold values. In addition to base flow metrics, as we saw in other data, there's a need for timing of events as well as low flow conditions. This method can serve as a guideline for setting seasonal thresholds and for timing, duration, and frequency of those events. In addition to identifying the effects of flow parameters on mussel presence, we also determined how mussel life history traits might aid in adaptation to different flow conditions. We found that species like Amphicynus and Macrodon that represent R-selected species were more likely to be found in watersheds with higher landscape and hydrological alteration. Given the rapid lifespan and early maturation, these traits likely explain why these species can maintain presence in heavily modified streams like the Trinity River, which has significant alteration and frequent extreme high flows. The ability to quickly recolonize likely contributes to their continued presence. Conversely, Randklev is much more prevalent within the least modified system. Given the long lifespan and lower fecundity, Randklev represents a K-selected species with traits that are not conducive to coping with unpredictable environmental change. We also see that the Neches River more closely represents the natural flow regime with seasonal ebbs and flows. We can hypothesize that species like Randklev would not be well suited to areas with higher hydrological alteration and this species could be at higher risk of decline with increased urbanization. We have demonstrated that these methods could be useful for the potential management of freshwater mussels, but beyond that, these methods could be applied to any aquatic species of interest. These methods can be used to identify and set potential thresholds for minimums, maximums, and timing of events to better manage the life cycle of most aquatic organisms. Moving forward, these methods could also be applied to a greater number of rivers that represent a larger gradient of landscape and hydrological change, and to a greater suite of species that exhibit other life history traits. These methods could also be applied to manage species with limited knowledge based on common life history traits, and could be useful for the continued management of a number of threatened and imperiled species. At this time, I'd like to thank the Texas A&M Natural Resource Institute for allowing me to come and conduct research that will benefit imperiled aquatic taxa, and our partners, the Texas Parks and Wildlife and U.S. Fish and Wildlife Service, for funding and support. I'd be happy to answer any questions via email at alex.kiser@ag.tamu.edu. Thank you.